Today we're going to talk about inducer draft motors or inducer fan motors. These motors are essential to the modern gas furnace. The new gas furnace has the heat exchanger where we're pulling the flame horizontally through the heat exchanger. This motor is actually pulling that draft through the heat exchanger to make that happen. If this motor fails, we'd have a catastrophe. So we also include a vacuum pressure switch that ensures this motor is working. Before we used vacuum pressure switch, they actually had a centrifugal switch. But the centrifugal switch just said the motor was working. It didn't say if we were pulling a proper vacuum to this pressure switch. Proper vacuum to the pressure switch means I'm also pulling the proper vacuum through our heat exchanger to make sure we have the proper air-fuel mixture. Now, a few important things about this motor. We want to make sure we have the proper voltage, the proper amperage, and we're pulling the proper vacuum. We're going to cover all those pieces of information, but first let's go into a little bit more detail about this motor. If we were to pull this motor out, we would see something like this. It's a whole assembly. So when this goes bad, you replace all this as a kit. What's nice about this particular model is we have these little rubber grommets. This allows it to absorb vibration, so it's a lot quieter for the customer's operation. This is our little miniature blower wheel, so it's actually pulling a draft to the center, and it helps start a draft to the top side. Very simple little motor, but if we take a look at the same exact motor under different conditions, we see there's a good amount of corrosion on here. This corrosion is very important for us to see as technicians. If we see this corrosion, it tells us that we have one of two problems. Either we have moisture coming in through the flue pipe, or even worse, we don't have the proper combustion analysis going on. We don't have the proper amount of combustion. A byproduct of combustion is water vapor, or H2O. That water vapor, H2O, will build up on this blower wheel. It'll build up in the flue pipe, and even worse, it builds up in the heat exchanger and actually eats the heat exchanger away from the inside out. These are type 1 furnaces, so we need to make sure that our flue gas temperature is above dew point. If we draft it too fast, we'll actually take away too much heat and that water will condensate. That condensation is horrible, and if we see that on this motor, it's a red flag that we have a big issue going on. So seeing the condition of this wheel is very important. But another thing we have to take into account is when we pull this motor off, we got to make sure that we are very careful with the gasket. This motor has a rubber gasket, but at the very bottom it's been ripped, it's been torn. Most of the modern gaskets use a type of fiberglass insulation as a gasket. The insulation of that fiberglass handles the high heat. So if we were to pull this motor off, there's a very high chance that we've actually damaged that gasket material. So we want to be careful with that. So instead of pulling this motor off and checking it every time, there's a simpler method. We can actually look in the very end and we can see what's happening with the blade. If we're working on a furnace, I would take this vent pipe entirely off, take my flashlight, look down inside of here, or even better yet, I could use an endoscope that attaches to your phone and you can get a better view of what it looks like. So knowing the condition of that inducer wheel is going to tell us a lot about the condition of this heat exchanger. For example, this wheel, we have a significant amount of corrosion. So we have some kind of a moisture issue, either coming from the flue pipe or improper combustion in that heat exchanger. So these are some very important things. But also, we have cracks here, and this plastic piece is even broken. Now this is a composite type material made to handle a significant amount of heat. It's very sturdy plastic, but what happened was the roof had been replaced. When they replaced the roof, they lifted the vent pipe up, and when they did, they shoved the vent pipe back down when they were done. That extra force caused this to break. So these are things you need to take into account when you're working in your customer's house. Has there been a hailstorm in the area? Has their roof been replaced? You want to check the vent pipe in the attic to make sure it's still in good shape and make sure nothing's damaged, for example, like this one was. So these are things that we look for, as well as this pipe condition here. Another example we have is this one. Notice it's very sooted up, extremely black. We compare it to this one, and we can see a significant difference in the condition of this blower wheel. What happened with this particular situation was the furnace was running on propane. The furnaces come naturally from the factory for natural gas. Running this on propane gives you the improper air-fuel mixture, the improper spuds were used, improper gas pressure is used. Even though it ran for a short period of time, it sooted up all of this entire inducer fan assembly. But the problem is it also sooted up inside the heat exchanger. That's not covered under warranty. It's very difficult to clean that out, and you probably will never get it back to factory conditions. So it essentially killed this gas furnace. If we look through the tube on the end, we can see all of the black inside of the blower wheel without having to fully remove it. If you can see this one, we ended up with a lot of gasket material left over, which means once this was pulled off, that gasket would have to be replaced, but in this case, it's most likely going to be a new furnace. As we're talking about these inducer fans, there's something else that's very important. On the back side of this inducer fan, there's going to be a hole. This hole is called a restrictor plate. It's a very precise size. If we engineer, they know the size of the wheel, how fast this wheel is turning, and if they have a set size hole here, they know exactly how much air they're pulling through that heat exchanger, which is very important for combustion. If we know exactly how much air we're pulling through here, we can adjust the gas pressure and get a proper combustion. Here's an example of some replaceable restrictor plates off of other units. This one's rated for 1.750 in size, and this one is a 1.938. This one has a significant amount of carbon built up on here because when we pulled this one off, we found that somebody put the wrong plate in its place. That caused incomplete combustion and caused the heat exchanger to die a short death. So if you ever pull this heat exchanger off or the inducer assembly off, you want to make sure you go back with the proper size restrictor plate because it can definitely affect the entire operation of these gas furnaces. What we're going to do next is we're going to fire the system up. We're going to check the amps with my top and we'll check voltage at the bottom. Remember, we need to have the proper amps without overamping, the proper voltage, and also we want to make sure we're pulling the proper vacuum to that pressure switch. So I'm going to have it call for heat. The amperage I'm pulling right now is 1.15 amps. I check on the motor and the motor's rated for 1.8. 1.8 is my max. I'm at 1.1, I'm well below my max. That's a good sign, that's what we're looking for. In addition, I want to check to make sure I have the proper voltage to my motor. Low voltage or high voltage can tell you have some other issue either with the system or the power in the house. So I'm just going to move my instrument ends, my leads, so I get good contact with the metal, and here I'm showing 123.6 volts. So that's good. I'm within the range of voltage needed for this motor. The motor has on it printed what the maximum amps are, and usually has a voltage range on there as well, which is usually 10% of rated. So we know we have the proper volts, we have the proper amps. Now, is it pulling the proper vacuum? So let's check that next. What we have here is a digital manometer. This is what we're going to use to check the pressure. So I'm going to turn this on, and the next thing I do is zero it out. To check pressure, we're pulling a vacuum, so this is going to be negative pressure. I have this nice little T, and I'm going to take the hose loose that we have, connect it on my T. The existing tubing I have, we're going to put onto the collector box. And we're pulling 0.22 inches of water column. This pressure switch closes at 0.2 inches of water column. So we are pulling just enough vacuum to the pressure switch for the pressure switch to close. So we are pulling enough of a vacuum with our motor. We have the proper amperage without overamping, and we have the proper voltage. The next thing I do is shut the system off, look inside the flue pipe to make sure that that motor and that wheel is in good shape. So if the motor's in good shape and it's pulling the proper vacuum, your next step would be to check the pressure switch. You would check to see if it's open or closed. How we can check that very simply is with our meter. If I get any kind of voltage at all, the switch is open. If I'm showing 0 volts, the switch is closed. So my bottom number is reading voltage, one on one side, one on the other, and I'm showing 27 volts. So that means that this switch is open. I'm pulling enough vacuum to the switch, but the switch is not closing. So now I need to look at the switch and see what's going on with that. Another thing that's likely to fail on these little inducer fan motor assemblies is the bearings. There's a lot of heat going on through here. It's pulling all that hot gas out, and these bearings are notorious for failing. Most of them are non-serviceable, non-oil bearings. So an old timer told me you could take your screwdriver, put it up against the motor and against your ear, and you can hear the condition of the bearings. And it's true. That absolutely works. But when I had a customer come up to me while I was listening to the bearings with a screwdriver to my ear, they thought, what the heck is wrong with this guy? And I tried to explain, but it was just really awkward. So now I've learned that you can buy these automotive stethoscopes that work really, really well. Put it in your ear, put it up against the motor, and you can literally hear the bearings turning inside. I can't describe what a good bearing sounds like. Once you hear enough motors and you hear one that's bad, you will know, wow, that is significantly different. We have an issue going on. Now, the reason I want to go through that extra step, which doesn't take very long, is because I don't want that bearing to fail in the middle of the night, Saturday night, 2 in the morning. I don't want to go back out because I did a maintenance call and I didn't check that bearing. So if I hear that this bearing is starting to go bad ahead of time, I can tell Miss Jones, we've checked the bearings and we're starting to have wear in these bearings. I recommend that we go ahead and replace this now before it becomes an emergency situation later. Now you can do it on both of your schedules instead of having to go out an emergency call in the middle of the night because she doesn't have any heat. Little things like that can go a long ways. So we know we have the proper voltage, we know we have the proper amperage, our bearing sounds good. Now let's check to see if it's pulling the proper vacuum. To do this, there's a little hose on the back of the collection box that goes to our pressure switch. I have my digital manometer and a T that I'm going to use. I'm going to unplug the hose to the pressure switch and plug it into the T. Then I'm going to take the hose from my T, plug it into the collection box. Now my manometer is reading the inches of water column. So I'm pulling 0.22 inches of water column for this furnace. I should be pulling 0.3 inches of water column for my pressure switch to close. So people say all the time, is it my pressure switch or is it my motor? Well, in this case, I can tell you for sure that the motor is not pulling enough of a vacuum to my pressure switch. So my switch shouldn't be closing. I have an issue with my motor, which could be the motor, it could be the wheel, could be the heat exchanger, but my issue is on this side. My next step would be to shut the system off and then pull this motor out to physically look at the heat exchanger and physically look at the wheel. Now it's worth the risk of checking that gasket material. So another thing we can do for the pressure switch to ensure that it's opening or not is check voltage. If I read 0 volts, the switch is closed. If I read any voltage at all, the switch is open. There's the potential for flow, but it's not flowing. So I have my meter on volts, the bottom number will read volts, the meter on one side and the other, it doesn't matter which direction, and I'm reading 27 volts. So because I'm reading voltage, my switch is open. I know I'm not pulling enough vacuum for the switch to close, and I've checked and my switch is open. So it's not a switch problem, I have a problem with my fan. Now before you can dim that fan, you also want to check these little rubber hoses. They're notorious for getting dry rotted and cracked. So I would pull this hose off and inspect it. All of these steps are essential for working on these inducer draft motors. When I pull this motor off, it comes to a nice slow stop so we can actually hear what's happening. But I want to talk about some other very important pieces of information for this inducer draft motor. One of those information is this style right here. We have a double wall vent pipe. This gas furnace is a category 1 gas furnace. A category 1 gas furnace means this is negative pressure, non-condensing. That's essential. Category 1, negative pressure, non-condensing. That means this gas furnace is natural draft. It's a naturally drafting out. If you hook the manometer to this, you would see that it's negative pressure. It's because of the natural convection. As the molecules are moving faster, they're becoming less dense and lighter, and they're traveling up and out of this flue pipe. This fan motor does not force the combustion gases out of this flue pipe. I've had technician after technician claim that because it has this inducer fan motor, it's forcing the gases out, and that's simply not true. You need to read, and if it says it's a category 1, it is a natural draft. Now they do make a few category 3, still non-condensing that's positive pressure, but they're very far and few between. Read in that furnace and see what category it is. So if it's a vent pipe like this, it's very important we note that. I've also seen customers take and put heat exchanger material on their vent pipe to try to get extra heat out of their furnace. It sounds like a good idea. What happens is they cool this vent pipe too much. That causes condensation to happen because we drop the temperature below dew point, and that comes back and rusts out our flue pipe, rusts out our motor, as well as rusts out our heat exchanger. These are things that's very important to keep in mind. The other type of furnace that we see most common is our 90+ condensing furnace. We have a plastic housing. This is because there's going to be condensation inside that heat exchanger. So we have a plastic blower wheel, and we have a plastic housing. This allows it to handle that water, and a lot of times that water, that condensate, is corrosive, so it has to be able to handle that. But this is a Category 4 furnace. Category 4 says it's going to be positive pressure and also condensing. This is going to have a PVC flue pipe. The PVC runs completely outside. The PVC can handle the condensation, and it can handle the pressure without losing any carbon dioxide or any combustion gases into the house or the living space. So a Category 4 will see this plastic style vent pipe. On top of that, this particular motor is unique because it's a 2-speed motor. Instead of having 2 wires going to this motor, we actually have 3. So we're going to use black and common for high speed, or we use red and white, which is common for low speed. So we're going to use one at a time. So if you wanted to know if it's on high speed, you would clamp the meter around it. 0 amps means it's not using it. And if you check that on low speed and you get a number of amps, you know you're on low speed. It's a very simple way to check it. Some of the new gas furnaces are now even a step above that, where they have electronically commutated motors, which means they're full variable speed for a modulating system. Those get into a whole other aspects of checks and maintenances. But this is our inducer motor, Category 4, plastic, positive pressure, condensing, and our other most common that we see is Category 1, negative pressure. Now on that, if we have this vent pipe stop up, it doesn't mean that we're going to have an issue with our pressure switch. We could have this entirely stopped up, leaking carbon monoxide gases in the house, and the furnace still be working. A lot of manufacturers will have this. This is a draft hood connector or a draft hood limit. In this case, there's actually a hole inside of this. If the gas pressure backs up, it will back up and start leaking carbon monoxide and combustion gases across this, which you think, oh my gosh, that's a problem. And yes, it is a problem, but the reason is we have this limit switch here. So as these gases back up, it's going to push these hot gases across this limit switch, and this limit switch will trip, shutting the system down. And just like a rollout, this is manual reset, which means it's not going to automatically retry. It says, hey, if this tripped, we have a big problem. Somebody needs to come out and inspect our furnace. We need to inspect the flue pipe. We need to inspect the top. We need to inspect the cap. Seen it where it's had bird nest, bee nests inside of it, or hailstorms completely crushed the cap, and we can't get the flue gas out. So these switches like this are very important. Not every manufacturer uses them, but it also goes to show you that this is negative pressure, natural draft. It's actually pulling air in through here. If air starts coming back out of that, you know you have an issue with your exhaust or your flue. The pressure switch. Why is it there? How does it work? And how do we check it? That's what we need to know today. The sequence of operation thermostat calls for heat. Sends 20 volts to IFC. The IFC does a safety check. The IFC closes a relay, sends 120 volts to our inducer fan motor. Our inducer fan motor pulls a draft through the heat exchanger. It also pulls a draft or pulls a vacuum to our pressure switch. Our pressure switch closes, sends 20 volts to the IFC. It's essential that we have this motor working, and we don't just want to assume that it's working. We need to know without a shadow of a doubt it's working, and that's why our pressure switch comes into place. Our control board just sends a relay, closes the relay, sends the voltage to this inducer fan motor to work, but it doesn't know if it's doing its job. What we have here is our vacuum pressure switch. As this motor's running, as it's pulling a draft through the heat exchanger, it's also pulling a vacuum to the switch. The switch closes, 24 volts goes back to the IFC. We know for sure that this motor is working. In the old days, they had centrifugal switches on these motors. So when the motor spun fast enough, the switch would close. The problem we had was these old motors would rust out. There'd be some kind of an issue with it. The switch would close, but it wasn't actually pulling a draft. The flame would roll out of the heat exchanger and catch the system on fire. So this was the better system that was invented. As this motor is pulling a draft, doing its job, it pulls a vacuum to this pressure switch, switch closes, tells the IFC it's working. So my students, to make them understand, I have them say it as a negative pressure switch or a vacuum pressure switch, so they understood that it's sucking, it's pulling a draft against the switch. It's also its job is to watch this motor, so to speak, to make sure it's doing its job. If this motor stops working, it tells the IFC, hey, we got a problem, and the IFC shuts everything off to make sure we're running safe. So some of my students, they call it a vacuum pressure snitch because its job is to watch him and snitch on if there's a problem. However you need to remember that, it's a massively important safety feature. So how it works is quite simple. Inside, there's a type of diaphragm in there, and there's also a micro switch on one side. So when we pull a pressure difference on one side, the atmospheric pressure pushes on the other. What it does is makes the switch close. It physically moves the contact with this piece here. But if we see, this diaphragm fitting is very fragile. It's very thin type of material, so it's very easy to break. Over time, they can break or get worn out. They can crack, they become brittle, especially if you have condensation in there, which you shouldn't have. That can build up in here and cause severe problems with these. It's important that when you're checking this, you don't put your mouth to that tube and suck on it. I've seen people that check them like that, but the problem is you pull too hard and it does what happens to this one. It actually rips this diaphragm. The other thing is you have combustion gases through here, poisonous gases through here, and you don't know what's inside of this switch. So as you're sucking on that, you're pulling all that stuff into your lungs. So it's not a good idea to use that. We want to check it the proper way. So let's talk about checking it the proper way. This switch, we need to think about it as a pressure and a switch. So we need to make sure, do we have the proper vacuum coming to the switch first? Then if we do, let's see if the switch closes. So we're going to fire this system up and go through that process. But how are we going to check to make sure we have that happening? What we're going to use is this nice little brass T. I'm going to unplug the hose existing and I'm going to connect it to my brass T. The other hose on the side is going to go back to my inducer fan motor, my inducer draft, so it's pulling a vacuum. That's also going to pull a vacuum to this and this third hose. In the old days, we used to use a magnet helix. I would use the low pressure side, and as this ran, I could see how much of a vacuum it's pulling in inches of water column on this tool. The problem with this tool is, over time, they get out of calibration, you gotta have them recalibrated, and they bounce around in the truck, and it would make them inaccurate. So now we have digital manometers. This is the way to go now. We simply plug this in, and if I want to calibrate it, I just press the 0 button, it zeroes it out, and I'm ready to start. So what we're going to start with is see, is the switch good? Is it bad? Are we getting enough vacuum? My control board, the switch, is it closing? What's happening? Let's find out. We're going to have a call for heat and go through our sequence of operation. Now our inducer fan motor is working, but we're pulling 0.1 inches of water column. This switch is rated at 0.25 inches of water column. So the switch right now is not going to close because I do not have enough vacuum going to it. 0.10. The switch should be open, which means I should read voltage. Let's check. I'm reading 27 volts, so I know my switch is open, and it should be open. You could think, well, the switch isn't closing and I want it to close, let's replace the switch. That would be wrong. That's like saying your gas gauge is on E, I need to get a new gas gauge. Do you have gas in the car? In this case, we need to be thinking, my switch isn't closing, it's a vacuum pressure switch. Do I have enough vacuum? And the answer is no. I only got 0.1 inches of water column. In this case, it's jumping around a little bit, but 0.1 inches of water column. I need 0.25 inches of water column for this to close. So I need to be looking on the fan side. What's going on here? Let me check that inducer fan motor, go through all that process to make sure that's working first. It's not a problem with my switch. It's on this side. So I'm going to make a minor adjustment to this unit. Now we can see I'm pulling 0.34 inches of water column. It closes at 0.25. There's two ways I can now see if that's working. One way is I can look down and see if my hot surface igniter starts getting hot. The other thing I can do is check voltage. With the switch closed, I should have 0 volts. Put the meter on one side and then the other, I'm showing 0 volts. So the switch is now closed, and down below our hot surface igniter is getting hot. So we know that that can't happen until the switch closes. So that's a good sign. As I cycle the system off, my inducer fan motor cycles down and I start losing my vacuum. The switch then goes back to its open position. It knows that it should be open. The control board knows that it should be open. Everything is working correctly, as it should. That's one way to check the switch. There is, however, another way to check it. What we can do is we can pull these wires loose. And I can have a call for heat. And with my manometer, I know I'm pulling the proper vacuum. I can then take my meter and turn it to ohms. OL, infinite resistance, open. And if I touch the terminals together, I got zero resistance, closed. If I check across the switch, I'm showing 0 ohms of resistance. My switch is closed. If I shut my fan motor off, I lose my vacuum, the switch will close. So if we check the resistance now, we show OL, the switch is open. Two different ways of checking the switch. I prefer the voltage method because it's faster. I don't have to pull wires loose or worry about wires connections going bad. There is a third way of checking this. This particular model of manometer has a pump built into it. So what we're going to do is we're going to set that up next. I'm going to take this hose and the T off. We're going to put these adapters on. I put one hose on pressure port 1 and one hose on the pump. Then we're going to put an electrical connector adapter on the very end. This cord just has 2 plugs. We plug one into one side of our pressure switch and one into the other side. Now what I'm going to do is turn the pump on for test mode. So I press test. It's going to do a 13-second countdown. At the end of that countdown, I'm going to then hook up the T to my vacuum pressure switch. I'm going to then increase the pressure until my switch closes. Here there's a little word that says close and a light above it. Once this light goes off, we know that that switch is without a doubt closed. Right now we have 0 inches of water column, and I'm going to plug my pressure switch into this T. So here I have 0.1 inches of water column. The light is off. So I'm going to increase my pressure. So I'm going to press the up button, INC, increase. Now I'm at, we got to make sure we're not kinked. My hose is kinked there. So we're at 0.2 and my switch is still open. So we're going to increase it even more. And now we're at 0.25 and my switch closed. So know that my switch is good. It closed at 0.25 inches of water column, and that's what the switch is designed for. So my switch is working 100% correct. So it's another way of checking the pressure switches. Now most of these pressure switches are NO. NO stands for normally open. So if I check these two, they're normally OL, infinite resistance. If I check it on the unit, I have 24 volts or some kind of voltage. But not all of them are normally open. They do make some that have normally open and normally closed connections, such as this one. The control board for this particular unit to know that the switch is for sure closed and the switch is for sure open. In other words, right now the system is off. It wants to know that that switch is closed, and when the system came on and pulled the proper vacuum, the normally closed would open, the normally open would then close. Without a doubt, the control board would know that this switch hasn't been bypassed. I have seen people try to bypass these, and you never want to do that. At the end of this video, we're going to show you what happens if this motor is to fail and it was to be bypassed and how dangerous that can be. So you never want to bypass that. I prefer to always go back with the manufacturer's OEM pressure switch, but nowadays I hear that they do make a universal kit that you can adjust and change the springs to match exactly what's here. But if you use that, you must make sure that you put the exact amount of pressure. This one closes at 0.25. I want to make sure without a doubt that my new one closes at 0.25. The other thing you want to check is these hoses. The hoses that connect it become brittle over time. They can be cracked, they can pull air in, and that air can make the switch not get a good seal. So you want to check this, and also sometimes this little tube where it connects into this inducer draft can clog up with rust or other contaminants. So you want to make sure that's in good shape. I used to keep extra hoses with me just in case that they cracked or broke. I can replace them and not have to worry about it. So just to recap, it's a safety device that makes sure this fan motor is working. Most of them are normally open. They close when we have the proper vacuum. To test it, the method I prefer is a T and a manometer, and check to see if the switch is open or closed with voltage. If I'm reading 24 volts, the switch is open. If I'm reading 0 volts, the switch closed. Very simple. Don't suck on it. Don't pull too much pressure on it. You don't want to damage it. And if you have to replace it, go back to make sure it has the exact same inches of water column that it closes for. So you can see there's a significant amount of time before the rollouts actually tripped on this furnace. That's how important this inducer draft motor is. We can see that there's a lot of charring going on. These wires have melted. They've melted here. There was a flame here because there was a small gas leak here to where we didn't put new pipe thread compound on there to seal it. It burned all the way up to the top, and even our limit switch failed. It's all melted. The furnace is still running right now because these limits have tripped. They're manual reset. So if we push the button, we can hear them click. And 2 of the 3 had tripped. But before they tripped, we still had a lot of scarring going on. I've heard people say, hey, it's okay to bypass that safety just for a little while because there's other safeties on there. And it's simply not true. These other safeties are there, but by the time these safeties tripped, it was already too late for this furnace. So you don't want to rely on just one safety. You don't want to bypass any safeties at all. They're all there for a reason. Never bypass a safety. They're designed to keep the customer safe, you safe, everybody safe. Also, I want to show the importance of these limit switches. If they trip, that's significant. So if those limit switch trip, you need to find the cause of it. And again, this is why we like to stand to the side of the furnace when it ignites. Because if you were standing here in the front, something happened, it ignited, that flame comes out this direction, lose your eyebrows. So make sure everybody's safe. Don't do stuff like this. Don't bypass safeties. Make sure everything's working by the manufacturer's specification. If we pull this inducer fan motor out, you can see there's a lot of black on here and all around here. That's because this unit's running on propane right now and it's designed for natural gas. So it's a huge issue. You should never do that. We're breaking all the rules today. You can see all the soot built up in here. It's also building up inside the heat exchanger. And there's a ton of soot built up on this wheel right here and all through here. So this only ran for a few minutes with the wrong gas and it did this much damage. So when a furnace runs without the proper gas air fuel mixture, without the proper conversion kits, these furnaces die a very early death, and that is not covered by any of the manufacturer's warranties. They say specifically in the manual that you have to follow the certain guide and their steps for converting these over. And also, many states require a separate certification for propane conversion. Texas requires you to go through the Texas Railroad Commission, and each state has their own requirements and regulations. And that's because of the significant damage here. This thing could run, the whole heat exchanger could soot up, and I've seen the flames come out of the heat exchanger, burn up the whole entire furnace just because they didn't have the conversion kit. Be safe, do it right.